Time is an illusion, lunchtime doubly so, as Douglas Adams famously wrote. Time is a concept that has always fascinated us. It can flow like a river or trickle like a stream. On a busy day, it seems to rush past us. Yet as we wait for a bus, a minute can take forever. But what exactly is time? Is it an absolute flowing entity? Or is it simply a relation between when you put bread in the toaster and when toast pops out? How we view time has profound philosophical impacts on the way in which we approach science. I am Ankita Anirban, and I am speaking to Professor Frank Arnsenius, Sir Peter Strawson Fellow and Professor of Philosophy at University College, Oxford. Professor Arnsenius holds undergraduate degrees in both physics and philosophy, and a PhD in the philosophy of science. His research interests are in the philosophy of physics and decision theory. His book, Space, Time and Stuff, was published in early 2012. In this, he discusses a number of ideas about the structure of space and time. So, was there time before the universe started, for example with the Big Bang, or did time come into existence with the universe?
So my answer is basically, no, there was no time before the Big Bang started, but it depends on the details of general relativity, that answer. One could, in principle, have something like a Big Bang theory set in a Newtonian space-time. So it could be that there was one point in time in which everything was concentrated, well, near to a point, and then it exploded out and was bigger and bigger. In a Newtonian theory, well, there is just, because of what a Newtonian theory is, there's always space and time. It doesn't come to an end. So there would have been time before the Big Bang occurred. But general relativity is quite different because it says that the structure of space and time depends on the matter that there is. They're interrelated. In particular, there's curvature where there's matter. And in particular, if you look at general relativity, at how presence of matter affects the structure of space-time, what you find is then that as you go back closer and closer to the Big Bang, the matter gets closer and closer together and produces a stronger and stronger curvature. And in fact, the more closely you get to the Big Bang, the curvature gets bigger and bigger. And then if you then try and extrapolate it backwards to this moment at which the Big Bang occurs, you find that the curvature goes to infinity, which really means it makes no sense. That's to say, there couldn't have been a space-time fabric that satisfied the standard equations of general relativity plus all the matter in the universe concentrated at a single point, because the curvature at that point would have been infinite. That makes no sense. So the answer, we have a good reason to believe that there was no sense to be made of space and time at the moment that supposedly all of the matter was literally at a point. So it's wrong to think of the Big Bang starting at a point. Rather, the right way to think of it is space-time has a finite size. There just is no space-time at the moment at which the Big Bang singularity occurs. Or to put it another way, you cannot, while satisfying the equations of general relativity, extend space-time beyond the Big Bang. So we have good reason to believe there was no space and time. It's not that it makes no philosophical sense, it's that the details of the physical theory tells you there couldn't have been space and time before the Big Bang. But I have to also say that this kind of inference is based on classical general relativity, so not using quantum mechanics. We don't have a decent theory combining quantum mechanics and general relativity, and it may very well be, as lots of people have speculated, that what's actually happening is that you have a bouncing balloon type universe where before the Big Bang there was another period of expansion. Then before our Big Bang there would have been space and time, maybe multiple space-times that are disconnected through this quantum version of a singularity. But if you look at classical general relativity, then the answer is no, there wasn't space and time before the Big Bang. But who knows what will happen when you apply quantum mechanics to that? That's hard to say.
Could you please explain the difference between absolute time and relational time?
Relational time is the idea that there is no such thing as space and time as an object that's separate from matter and fields that live in this space and time. All there is are relations between events of the form, this event was 5 seconds later than that event, or this event was 5 meters distant from that event. But one should not understand on the relational view, when I say this event occurred 5 seconds after that time, I shouldn't think that that's true in virtue of the locations in time that they occupy, because there is no such thing as time. There are merely relations between events, just like there could be a father-son relationship without there being a space in which these things occupy the father position and the son position. At first sight, it seems like a bit of a strange debate to non-philosophers, Even though I've said, explain what the distinction is between the two, you might think, I have no clue what this guy is talking about. What is the distinction between saying that there is space and time or saying that there's merely a relation between events? But here's a way in which you can understand the distinction. In fact, let me talk now about the relational view of space. If you thought that all spatial relations between, let's say, objects at a particular time, like a particular distance, were due to the positions in space that they occupy, then there would be a big difference between the world that is the way it is now and a world which is just like the current world, except that everything is shifted 5 meters to the right, because they would occupy different positions in space. The distance between everything will be the same if you shift everything 5 meters to the right, but the locations that they occupy in space will be different, so it will be a different universe. On the other hand, on this view that I called relational, there will be no difference between the two, because on the relational view is all there is spatial relations between things. There isn't in addition this space where objects occupy locations in space, so those two worlds would count as the same. So in that way you begin to get a bit of a grip. You can get an even better grip if you think about the following question. Think of the issue as to whether it could be that the entire universe is rotating in space. On the absolutist view, well, there's a real fact of the matter. Are these things moving through space or are they not moving through space? If they are moving through space, they could be rotating through space. On the other hand, the relational view, it makes no sense for the entire universe to be rotating, because if the entire universe is rotating, all the distances would be preserved. So if you somehow thought that it makes no sense at all to speak of the entire universe being rotating or not, if you think that's a completely illegitimate, ununderstandable, silly question, then you're probably a relationist. If, on the other hand, you think, well, it could be that the universe is rotating, I'm not quite sure how I would know it, but it could be the universe is rotating, then you have an absolutist view of space. So that's a way of explaining, trying to get across what the difference is between those two views. One consequence of absolutism is it makes sense for the universe to rotate. A consequence of the relationist view is it makes no sense to say the universe is rotating.
So what are the arguments for the idea of absolute time, and what are the arguments for the idea of relational time?
For a long time, the tradition in physics and in philosophy was to believe that there is such a thing as space. When Newton talked about motion, he meant motion through space. He didn't mean change in relative position, change of distances. He meant motion through space. On the other hand, Leibniz, but he didn't have many followers, thought that no, all there was distance between things, and it didn't make any sense for the entire universe to be rotating. And then Newton responded to Leibniz by saying, well, look, but we can tell whether things are rotating or not. If you spin water in a bucket, you'll see that it's rotating by the curvature on the water surface, but it's not moving relative to the bucket. It must be that the reason why the water has this curved surface is that it's moving relative to space. For you, Leibniz, who doesn't believe there is such a thing as space, this makes no sense whatsoever, so clearly you're just wrong, because there is a difference between a rotating bucket and a non-rotating bucket, and we can see it in the curvature of the water. Mach responded to that by saying, yes, that's right, but what matters is not the rotation of the water relative to the bucket. I agree that there is no relative motion between the water and the bucket, but the reason why the water surface is curved because it's rotating relative to the stars. So Mach maintained a relationist view. Einstein, by the way, was very much influenced by this, even though later on it turned out his theory wasn't really a relationist theory, his theory of general relativity. What is really interesting is that ultimately somebody here in Oxford called Julian Barbour and collaborators have developed a relational theory that makes quantitatively precise Mach's idea about curvature of water being due to rotation relative to the stars, or rather the other objects in the universe. What is a really interesting and rather surprising fact is that Barbour has pointed out is that we can even make sense of the universe as a whole rotating or not. Roughly speaking, if you take a water balloon and rotate it, just like the Earth, it will expand along the equator because of the centrifugal forces, or rather the centripetal forces that are needed to keep the water in place. Similarly, if the entire universe were rotating, and if the entire universe, or at least the matter in it, had a roughly spherical shape, it would bulge at the equator. Now, the universe doesn't consist of a bunch of spherically distributed matter, but the analogy in general relativity can be tested. And it turns out that if you do that experiment, that within very, very large degree of accuracy, we have evidence that the entire universe is not rotating, which a lot of people claimed supports this relational view, because after all, the relationist says it doesn't make any sense for the universe to rotate, so no surprise that the entire universe is not bulging at the equator, or the analogy of that in general relativity. But I don't think this is a telling objection, since the substantivalist or the absolutist can also explain this. In any case, the upshot of it is that it's still an unresolved issue. I happen to be a substantivalist or an absolutist, but I think it would take a bit long for me to explain why I'm an absolutist. But suffice it to say that it's still a live debate amongst philosophers and physicists as to whether the relational view is right or whether the absolutist view is right.
And do you think that time can exist without events occurring, or do we need things to be happening to measure time around it?
I am actually an absolutist. I don't think that time is merely a matter of change. I think, no, there is time, and even if there were no events, there could still be time. But let me give you an interesting argument. You might think, how on earth could you have evidence for that? So there's an interesting argument by the philosopher Sidney Shoemaker that imagined the following thought experiment, where people said, how on earth could you ever have evidence that there's time without events happening? He gave the following thought experiment. He says, look, suppose that you live in the following universe, admittedly rather bizarre universe. The universe is divided, let's say, into 3 different parts. And the following bizarre thing happens. For a period of 1 year, let's call them regions A, B, and C. In region A, 10 years stuff happens like normal, and then 1 year, all the events freeze, nothing happens. Things stay exactly in their position. In region B, this happens every 13 years. And in region C, it happens every 17 years. So if you're in region B, you see every 10 years, you see region A freeze for a year and then move again. Similarly, you see in region C, everything freeze every 17 years. You don't, of course, notice anything in the 13th year when you're freezing because you're also frozen. Nothing happens. But the people in 17 or in 10 see you freezing, or if you think, oh, I don't want to be frozen, you move from region B to C, then you see region B freezing. Okay. So we could clearly have evidence that this is the case. It's a bizarre world, but we could have evidence that that is the case. But once we know that A freezes every 10 years, B freezes every 13 years, C freezes every 17 years, we can immediately figure out that once in every 10 times 13 times 17, which is, I think, 1391, it doesn't really matter what it is, but you multiply 10 by 13 by 17, we can figure out that every, whatever it is, 1391 or so years, the entire universe will be frozen. So there are no events. But we also have good reason to believe that time will continue, because when part A freezes, it's not as if time stops, because things keep happening everywhere else. When region B freezes, it's not as if time stops. It seems that we have at least some reason to believe, no, it's not like time stops when the events everywhere stop. It's just that once every 1391 years, the entire universe comes to a standstill, so there are no events, but time doesn't stop. So he said, this is how we could have empirical evidence that there can be a flow of time even when there are no events occurring, because everything is frozen. That's merely a thought experiment. The reason why I believe that in fact this is true of our universe, even though I also believe that in fact there never will be a moment in which there are no events occurring, is a bit more complicated. It has to do with these arguments for absolutism.
But surely against this zone A, B, and C argument, you could argue that the only reason we know that time stops for a year in zone A is because there are things happening in zone B and C. So you have those observers to note that everything's frozen. Surely if in the 1391st year, if everything was frozen, then what would it mean for time to go on?
So clearly we can't have direct evidence for this, because if we're assuming that everything is frozen, that means that we're not gathering any evidence. And here's where philosophy begins to matter a bit for how you solve these kind of problems. So how do we think in general you solve problems like that? There's lots of things that we don't directly observe. We don't directly observe electrons. We don't directly observe genes. We don't directly observe very distant parts of the universe, but we have theories about it. So in general, we solve problems like that, and we have to do this in science all the time. We have to form opinions about things that we don't directly observe, can't directly observe, or haven't observed, by forming a theory and confirming or disconfirming theories. How do we do that? Well, the general strategy is we believe that the simplest explanation of those things that we have observed is likely to be true, or is likely to be approximately true. And the simplest theory in that little example, the simplest theory, it seems to me, about the ABC region universe is that time keeps flowing. It's just that once every 191 years, 1391 years, the entire universe comes to a halt, but that doesn't mean that time stops. It will be a bit of a strange theory that says, oh yes, some of the time little bits of the universe come to a halt, but the entire universe never comes to a halt. No, just once every 1391 years, something really strange happens to time. It just sort of It's not that the universe freezes, it's just that time comes to a standstill and then it starts to pick up again. In fact, it doesn't even start and pick up again, it just flows through continuously, but once every 1391 years we get an exception to the theory that says once every 13 years this region comes to a halt, once every 19 years this comes to a halt. So generally you give such answers, it seems to me, by looking at what the best theory is of the things that we have observed, and that can very often give us good reason to believe certain things about things that we haven't observed, including that there is time when no events occurring.
Thank you very much, Professor Arndt Zenius.